Before we begin, we have just a couple of little announcements. The good news, leave that door open so people know that this is going on. The good news, we got 30 more banquet tickets available. So if you have not secured a banquet ticket, go ahead and do it, okay? And this is pretty much it. We're sold out, and I'm sure these will sell out too. So you don't need to do it now. I don't think there's anybody there, and I've reserved one for you. Okay, and for our two French leaders, who I know needed them. Okay, that's another thing. The other thing is after the talks and after the science fiction panel, those of you who registered today with a credit card, please go to the front desk. We need to get the security code of the credit card. That apparently was not done. All right, our next speaker is Dr. John Grotzinger, who is the principal investigator of the Mars Science Lab mission. He is a professor at Caltech, and he's been involved with a number of Mars missions previously, the Mars Reconnaissance Orbiter, the MER rovers. And without further ado, Dr. Grotzinger.
Well, thanks a lot for inviting me to be here. It's a real pleasure. I know you guys are a group of enthusiasts like we are up at JPL, so it's always a pleasure, especially when you get to do it locally. One small correction is that I'm actually not the principal investigator. I'm what's known as the project scientist, and I work together with a group of principal investigators. In this case, there are 9 of them for MSL that have delivered various science payload elements for the rover. So we work as a team on this mission, and I speak on their behalf, and also all 423 team members. This is the biggest mission to ever fly to space that has to do with science. Okay, so we'll get started with a little bit of a mission overview. In something more than 2 days from now, we will land on the surface of Mars. We launched in November 26th. We had an 8-month cruise period. We launched on an Atlas 541 launch vehicle. If somebody's got a laser pointer, that would be great. Okay, that's good. And one of the things that the public is most attracted to about this mission is our entry, descent, and landing system, which features something called guided entry and sky crane. And really, I won't say a lot about this because I'm sure you've all seen the video, but I'll just point out for history's sake, the really 2 very distinctive components of the CDL system are the guided entry, which features movable ballast. So when the aeroshell enters the upper atmosphere, it ejects some tungsten blocks, which offsets the center of mass from the center of symmetry, allowing the spacecraft to effectively fly through the atmosphere as a wing. At the same time, there are 3 thrusters that are symmetrically distributed to give us control of this system, not us actually, to give the onboard computer control of the system to fly out of errors in the projected landing spot that are created by unknown issues having to do with atmospheric structure, winds, density differences, things like that. That's the first thing. The second one is the sky crane, which you can see here illustrated. I'm sure you've all seen this. This allows us to drop down this payload, which weighs about 1 metric ton, onto the surface of Mars and hopefully do it in one piece. And so the 2 things together have already created the greatest dividend for science, and that is to allow us, for the first time in the history of landed space missions, to actually pick our landing site. So we had many candidates. It was a 5-year selection process to arrive at the landing site. In the end, we came down to a final 4, which were the tops that were favored by all the scientists. We kept waiting for some engineering criteria to come along to kill 1 or more of these landing sites. They all survived. And so in the end, science got to pick where they wanted to go. That's the first time. Okay, so here's our sort of rover ancestry. You can see the little Sojourner rover here on the lower left, about the size of a microwave oven. MER gives us golf carts, and MSL Curiosity gives us SUV-sized vehicle that we put on the surface. Just quickly to go over the payload, I'm sure many of you have read about this, so I'll just summarize it quickly. We grouped the science instruments into 4 groups, and the instrument is in bold, and the principal investigator that was responsible for building that instrument is shown there in brackets. So we have remote sensing, which features cameras. This rover has altogether, it has 17 cameras on board, and 4 of them are science cameras that have color, telephoto imaging, video capture at 5 frames per second, and HD resolution at that. One of them will be the camera, the MARTI camera, which is listed down there at the bottom. We didn't know where else to put it in this group, so we stuck it down there. And basically the MARTI camera turns on slightly before the heat shield is dropped off the vehicle, and it creates a movie all the way to the surface. So all of the critical stages, we hope, on the first saw, you'll probably, if we're successful, you'll hear Mike Malin discuss 18 images that he has selected to return to Earth out of this enormous data set that will otherwise probably take us a month to download, because it's a lot of data. Okay, we have ChemCam that you've probably heard about. That's our laser-induced breakdown spectroscopy. It reaches out to about 7 meters in front of the rover, interacts with the rock to create a plasma, and then looking at the light spectrum tells us something about the chemical composition. Molly is our hand lens on the rover. Again, this time around it's color, it does video, HD resolution. APXS is the tried and true chemical analyzer that's flown on the previous missions. SAM and ChemIn are our 2 laboratory instruments that really distinguish this science payload from everything that came before it. ChemIn is X-ray diffraction. It sits in the belly of the rover, just behind, if you look at the CAD drawing there, behind the arm. It doesn't show up too well, but there's some inlet ports. Flap cover opens up, we drop the sample in, it goes into the XRD. The other instrument that we've got, sample analysis at Mars, is basically the instrument that's going to allow us to do a whole variety of geochemical measurements where we take a sample, heat it up to about 1,000 degrees centigrade, and look at the volatiles that come off, including any potential organics that might be present in the soils and rocks. Environmental characterization, REMS is our weather station, wind velocity, wind direction, ground temperature, atmospheric temperature, UV radiation, humidity, things like that. RAD, and by the way, we're hoping to develop an app that you'll be able to download and get the daily Mars weather report, which I'm actually really excited about. I'm pushing that quite hard, trying to get some major outreach going on here beyond just the images for once. RAD is our radiation detector. That's the one I'm sure you guys are the most excited about. This has already been operating since 10 days before cruise. Historically, what actually happened is that we ran into a bit of a problem with one of the rover compute elements, the onboard computer, and in an attempt to troubleshoot that, an opportunity came up and we actually turned on RAD earlier than it was slated to turn on. So within 10 days of launch, we were collecting data on the radiation environment in space that astronauts would feel if they were on their way to Mars. And when we land on the surface of Mars, we continue to collect data with RAD. Every hour on the hour, we collect 15 minutes worth of data in perpetuity through the whole mission to sort of understand how the atmosphere would attenuate the radiation spectrum. DAN is contributed by the Russian Space Agency, and that allows us to look into the subsurface to see if there are hydrogen-bearing materials there, either ice or water that's bound up in rocks and minerals. I picked one photograph that's my favorite of everything having to do with testing of this spectacular rover. There's just something cool about this. It almost feels like you could be an astronaut sitting in the chamber with this thing, getting ready to fly to Mars as your buggy to drive around on. Actually, what the guy's doing, this is in the thermal vac chamber, and that's a probe that he's got, and he reaches out to basically touch under Mars sunlight conditions what the thermal response is of the rover to the diurnal cycle of sunlight. Okay, here's the big technology that enables us to do all the sampling on Mars. This is a drill. It's the first time we've done drilling since Apollo. This time it's being done robotically. This drill is about 1.5 centimeters in diameter. It will penetrate down into the rock about 5 centimeters, and we collect the powder that comes out of the drill. It goes up the sleeve. into that chamber up there that's about the size of a hockey puck. And that's the first stage in the separation of the different grain sizes of the sample. And then it goes through a whole series of sieves, and we take the fraction that's less than 150 microns and dump that into SAM, and we take the fraction that's either less than 1 millimeter or less than 150 microns and put that into SAM, because SAM can take any grain size, but ChemMin really wants the fine grain material to do the definitive mineralogy. Here's at the end of the drill test. It's a percussion drill, and as a result of that, we're able to penetrate the rock at much higher rates than you would if it was just simply swirling around. Okay, these are images of the flight hardware, SAM and ChemMin instruments. On the right, that's the X-ray diffraction. The amazing thing about this instrument is that it fits inside a canister about the size of a toaster. So you take an instrument that would normally fill a room and you miniaturize it. And this is our first instrument on MSL that's basically gone commercial. It's already been licensed, they're selling it. The first application that it's found is in developing countries to detect anti-malarial drugs that obviously, something like mefloquine has a definitive crystalline structure. Stick it into ChemMin and you can find out actually what it's made out of, and it might be sugar. Okay, so SAM then is our quadrupole mass spectrometer and gas chromatograph. So the quadrupole, gosh, I wish I had a laser pointer, wasn't expecting this. Quadrupole is up there in the upper right, and then if you look into the upper left, actually all the way at the top is our sample carousel with 72 samples that we can potentially analyze. And then on the left there you see 6 coils if you look closely. And so this is a chromatograph, but it basically is a bunch of tubing that's basically wrapped around itself to give you the distance to separate out according to molecular weight. And all that fits inside a microwave oven for 90 million bucks. Okay, here's a picture I got to take. This was a great fun thing for me on the night before launch. I was able to sneak my way. My badge got me into KSC, and then after that I just followed the trail of the spotlights that are aimed up at the launch vehicle. One thing led to another, and I wound up actually there at the launch pad, and an engineer was coming off duty, and it turned out he had permission for photography, so he and I actually went behind the gate and stood up next to the rocket, and were about an hour by ourselves without another person around, and it was, man, it's about as close as you can get as to imagining what it would be like going to space. It was pretty cool. So the next day, picture-perfect launch. The science team was able to watch this at about 5 miles away, which is a little bit longer than usual because our power source is a plutonium-238. And so in the case of accident, they want to make sure that everybody's as far away from that as possible. But, oh, great, thanks a lot. Okay, so that's sort of the payload and the launch vehicle. And what I want to do now is do something that you might not normally hear in a seminar about an upcoming Mars mission. And because my background is really in earth sciences, and in particular studying the history of the early Earth, I wanted to give you a sort of an insight into what I really believe is going to separate this mission from all that came before it, which is that for the first time with the landing site that we chose, this is so important. One of the things about this landing site, unparalleled probably anywhere else on Mars, is the thickness of the stratigraphic record that we will explore at Mount Sharp. And with that, it's like getting into a time machine that not only takes us back, everybody knows that there are surfaces on Mars that are really old, but what you can't really do is go to some place on Mars that's really old and study it continuously in a record that might be hundreds of millions of years to 1 billion years in duration. So I want to give you a sense to try to appreciate that if you've never had a geology class before. So let's start off with this a little bit. I'm going to go all the way back to Mariner 9, a place called Nergal Vallis. And when the guys looked at this on the science team and the images first came back, immediately, as you all know, the speculation began about water on Mars. Now, at that time, they were debating whether or not it was water, maybe it was liquid CO2, maybe it was beer, you know, who knows what it was, but you can't be certain that it's really going to be water. Now, many decades later, we're all virtually certain that it must have been water in this case. There's just so much evidence for water on Mars now. You go to Viking, it looks the same, but it's just in more detail. And anybody that looked at this as a geologist says, what's happened is that a fluid flowed with enough vigor to erode the rock and form these channels. And so you could anticipate, long before the Mach camera ever came along, almost 20 years later, 20 or 30 years later, that if you conserve mass, all that stuff has to end up somewhere. And so there's a simple expression. I know there's some people in here that do science. I can't resist showing at least one equation. And basically what this says is that as a function of time, the change in elevation, you need to know anything about geology. This says it all. The change in elevation as a function of time is basically proportional to the flux of sediment in or out of some very small portion of the profile that the sediment's traveling along. And if the flux out is greater than the flux in, you erode. If the flux in is greater than the flux out, then you build it up and you get sedimentation. So it was no surprise, it's a spectacular discovery, but everything about what you just saw in the previous image, plus this relationship, predicted this. And so for me, this really begins the era in the understanding of Mars's surficial geological cycle that has to do with surface environments. And where you talk about surface environments, you can begin to talk about habitability and eventually what I consider to be the way a scientist would really approach the problem of looking for potential fossil life in an ancient rock. So this is a delta. Everybody in this room has seen a delta before. If you haven't flown over one, you've seen a picture. There's a major trunk stream that comes down, it divides in two, and then it splays out into 1,000 little endings here. This is Eberswalde Crater, which was one of our finalists, and we were very attracted to the site, and in the end chose Gale instead for reasons I'll mention in a minute. However, this is local. This is small scale. Turns out if you take all of the Mach data, and you go back, this is something that was done by Mike Kaplinger and Malin's group down there in San Diego. And basically what you see then are all these major outflow channels. And in addition to that, all the yellow dots indicate images where you saw something that looked like a channel. And what this global map shows you is that you're bounded by lines of latitude to the equatorial to mid-latitude ranges of Mars. So then what we did in my group at Caltech was to then take all the image data, Mach as well as mostly high-rise, and then do exactly the same thing, except now we're not looking for erosion, we're looking for deposition. And what you find here is basically that lines of latitude, again, bound the distribution of this. So what we saw locally in the Viking and Mariner picture, and then saw locally again in the Mach picture of Eberswalde Delta, we now know occurs globally. So this is really exciting because that put into context the discoveries we made on the MER mission, where we began to see layered rocks that for the first time were a couple of meters thick. And what we figured out here geologically is that if you look at this line, everything above the line is parallel to the line, and everything below the line is inclined with respect to the line. And you take the scale here and compare it to Earth, and this is basically what you get, is the understanding that this place on Mars, 3.5 to maybe almost 4 billion years ago, is pretty well analogous to what you can see here in the desert in Oman. If you dig down beneath a playa lake in between sand dunes, you see a fossil sand dune, which is all the strata are inclined relative to this master erosional surface, just like you have here, and everything above it is the wet stuff. And that's in fact what we discovered with MER. And so what we're doing is there's this paradigm when you teach geology that the modern is the key to the past. So we can look at ancient Earth and understand it based on the way processes work today. And now we're saying that the ancient past on Mars can be understood by the way that the modern works on Earth. And with this, then you open the door to some really neat insights about the early development of surficial environments. Okay, so let me take you back now to where I think we are in sort of the equivalent understanding of the Earth. And as we were discovering the Earth. And there's this guy, William Smith, and there's a great book that you can buy, really nice read, called The Map That Changed the World. If you're looking for a good holiday read, I highly recommend that book, and because it basically goes over William Smith's amazing discovery. And he was an engineer, civil engineer, that built canals in England. And as he was doing this, he sort of got bored with the construction and began taking notes. And he recognized that after a while, repeated patterns of the same kinds of rocks occurring over and over again. And so what he eventually did was to make a map, and part of that map was a cross-section going across England from Wales all the way to the White Cliffs of Dover over here. And all of these different rock units got a name, which is not the important part, Because what Smith recognized is that they all had different compositions. Some of them were coal seams, and what he recognized is that this map would be the key to the exploitation of the British Empire that would fuel the Industrial Revolution. So in the notes that come along with this map, he says, by constructing this map, I'm basically giving my country access to something that can help them develop as a nation. And man, was he right. So the interesting thing about it is, of all these names that are down here, this green one is the most interesting because this green one is given the name Cretaceous. And you've all heard of the Cretaceous-Tertiary boundary. So we now associate Cretaceous with a period of time, but it was first known here in England as a mineral name because Creta comes from the Latin, Cretaceous comes from the Latin word Creta, which means chalk. And so the cool thing about that is that right from the get-go, and early on in Earth history, in the mapping of the Earth, we recognized that minerals were very important for documenting the history of events. Smith was influential, and his nephew took up the cause after he passed away, John Phillips. And what Phillips did was to go around in other locations and recognize the same patterns. And from that, he proposed the first geologic timescale. And of course, before the discovery of radioactivity, nobody knows how old this was. It's kind of like us on Mars. And he recognized that there were 3 periods where these fossils that Smith had documented in these rocks tended to bend together over and over again, forming repeatable patterns. So we had Paleozoic, Mesozoic, and Cenozoic. And basically what you notice are these 3 peaks that are in here. Now what you have to do is sort of close your eyes and imagine now that you're on Mars, discovering the stratigraphic record for the Mars for the first time. And what are you hearing about in the newspapers, if not scientific journals? Clays, sulfates, anhydrous iron oxides. Maybe this is the time of clays. Maybe this is the time of sulfates, and maybe this is the time of anhydrous iron oxides. Wouldn't it be cool to find a place on Mars where you could go and go through the whole succession, just like William Smith did, and maybe unlock the keys to understanding the early environmental history of Mars this time? Okay, so just a little bit of a tutorial in how to understand geological time. Geological time scale has 2 components. There's a relative ordering of geological events. And then in addition to that, if we have things that obey the principle of radioactive decay, we can actually date them in absolute time. So in the beginning, basically what we do is we find some correlatable rock property. And on Earth, this is most often fossils. On Mars, we're guessing it might have to do with minerals. And what we discovered is that for the part of Earth history where fossils organisms haven't evolved yet to help us tell time, which is most of its history, the so-called Precambrian period, we use the isotopic composition of sedimentary materials to tell us about the passage of time. Then you combine that with some mineral on Earth. Our favorite mineral is zircon. This is like a time capsule. And it's got uranium in it, 238, 235, that decays to lead-206 and lead-207. And we can measure those isotope ratios and know exactly how old the rock is. And in a rock that's 3.5 billion years old, we get a precision of almost 100,000 years. So it's spectacularly good. And what we wonder is that maybe on Mars you hear about these goofy sulfate minerals. Jarosite's one of my favorites. You look at the formula, it's got everything in it. Most importantly, it's got potassium in it, which decays to argon. And guess what? On MSL, we could potentially measure that. And for the first time, have something other than impact craters to know time on Mars. So what we've done then in getting ready for the mission is pull together. I noticed you all had some books out here. Here's one to add to it. This is just going to be published this month, and it basically looks at the structure of sedimentary rocks on Mars. And what we propose in this book is to subdivide Mars and go around and look at all the stratigraphic sections, going to the very oldest places on Mars here at places like Nili Fossi. And then you go to younger places up here like Meridiani, which we studied with the Opportunity rover. And then if you try to find a single place where you might be able to get the whole thing in one go, this is like a big bootstrapping exercise. And if you want to find what's called like a key section, you try to find a place where you get it all in one go, and that's what Gale Crater looks like to us. So this was one of the major reasons why we chose this site, because at the bottom we get these clays. As we go up through the central mountain, we get sulfates. Then at the top, we cross over into a world that seems to be made out of anhydrous iron oxides. And if you ask the question, what in the world caused this great desiccation event on Mars, maybe we'll get some answers by going to Gale. So here it is. I'll just finish up with a little bit about the landing site now. Actually, the slide's a little bit out of date. This is our old landing ellipse. Our new landing ellipse looks more like this. It's 20 by 7 kilometers. We wouldn't move it anywhere else because we think the place we're landing in is so cool to begin with. But once we get done with that landing ellipse geology, we're going to take a trek that's going to send us up the flank of the mounds at least this far. And you don't have to be a geologist to recognize that there's some contact in here, and everything above is different from what's below. And this is where we go from the world of clays and sulfates into the world of anhydrous iron oxides. I think that'll be the biggest decision we make in the mission. If we ever get that far, we'll probably have a big debate about whether to drop back down and stay in the world of wet Mars, or whether to explore the world of dry Mars and try to ascend to the summit, which is doable based on the actual slopes. Think of this thing as Hawaii. You can actually drive up it with a rover. If you don't remember anything else about Gale Crater, it sits on the dichotomy boundary, and it's one of the lowest places on Mars. Geologists forever have wanted to go into Valles Marineris because it's a big, deep hole in the ground, and where there's a big, deep hole in the ground, maybe that's where water is, and you got all these sulfate minerals down at the bottom of Valles Marineris. Guess what? This is even a deeper hole. This is another several kilometers deeper than Valles Marineris is, and the base of the mountain here is full of these sulfates as well as the clays. It's interesting, just a quick note, this is something that Ken Edgett pointed out over 10 years ago, is that Gale belongs to a family of craters that show a progressive morphologic evolution from big Noachian age craters that were all filled up with some kind of material. And note here that Opportunity at Victoria Crater at the time is basically at the top of this fill. What we're proposing to do at Gale is go to the base of the fill because all the rest has been stripped away. So this is like getting into the interior of the planet to look at its most complete record. Okay, so getting close to the end here, we're going to land, we reckon, somewhere probably right about in here. The landing site features a big alluvial fan that probably dumped water and sedimentary materials right where we're landing. So we're really excited about this. And then when we're done, we're going to work our way up the mountain. Skipping ahead a little bit, I just wanted to point this out so I don't go over my time. This is our latest map that we've just made, and this is this alluvial fan. These dark lines are topographic contours, and the color means we're going up in elevation. So the water would have flowed out, you can see some ancient channels here, flowed out directly into where we've located the landing ellipse. And the landing ellipse is there because that's the safest, closest place to the mountain. It also turns out, we didn't really understand this fully until a couple of weeks ago, that we think we might be landing in sort of a jackpot of sorts with regard to the geology right there. So I'm going to toggle now between two different maps. This is a map now which plots a physical property called thermal inertia. And what the high thermal inertia values in red here may indicate is that there might have been water that cemented minerals that filled in all the pore spaces in the soils and the sediment particles that were there to make a rock that you might have actually had to use a hammer to beat with a little bit. So the cool thing about it is there's the topography, there's the high thermal inertia unit. This could well be some type of an aqueous deposit that we're going to land right on top of. Okay, so just to finish, summarize, I really feel that we've got an extraordinary science payload and vehicle to do the job. Gale landing site has tremendous diversity that we're really excited about. Ascent of Mount Sharp is going to provide us with the first high-resolution, long-term record of the history of another planet besides our own. And it's a big team. We've got 400 science team, and we're ready to get going. So thank you for your time. Okay, get a couple of questions right there.
Once you ascend Mount Sharp, that tells you about the sediment that happened after the crater occurred. is there any chance that after going up Mount Sharp, you could go up the crater rim and see what happened before the crater impact at the beginning?
Yeah, I mean, it all depends how long the rover's going to last. So, you know, what I, again, with you guys' sort of interest in mind, if you would have asked any science team member 3 months after Opportunity landed or Spirit landed how long those rovers were going to go for, we actually had a pool. And we were sort of, you know, people were guessing months. If you really went long, you'd guess a year. Nobody would ever guessed 8 years, not even close. And so if you ask now, with respect to this mission, which is designed to go 2 years rather than 3 months, who would have guessed that Opportunity would have still been operating when this landed? I sometimes wonder, maybe this rover will still be going when humans finally make it to Mars.
How did Mount Sharp form in the middle of the crater?
Great question. Very simply, that's what's the point of the slide that shows this morphologic continuum. And the simplest, shortest answer I could give you is that most of us think that somehow the wind blows across the surface of the filled crater, and the materials that are right adjacent to the rim are not as cemented as the materials that are closer towards the center. And so the wind acting over 1 billion or 2 billion years just excavates and creates a moat. Yeah. They were going to ask one. Maybe we can do one more.
Well, first, I find your calmness very reassuring. I'm ready to throw up right now. But I do have a serious question about, has there ever been a notion of actually sending an instrument to Mars that is miniaturized where it can do radioactive dating of the different players, the different kinds of isotopes that you can get that information?
We would love to do that. There's a collaboration between folks at Caltech, some of my colleagues there, Ken Farley and John Eiler, and some folks up at JPL, to basically propose an instrument and develop that. And you know, NASA's got it's a funnel process. It goes through stages of development until it's considered to be flyable. And so I do think that with the SAM instrument, with a lot of caveats in advance, we actually have the capability to do that because we can measure the daughter element, something like potassium, and the parent element, and measure the daughter as well. It might be possible for us to do a back-of-the-envelope calculation doing mass spectrometry of those elements. Okay, so I'm being asked to finish it up here. Yeah. Thanks.